Welcome to Lesson 2 in Math260. In Lesson 1 we considered basic definition of vectors, how to add vectors, how to scale vectors. Today we introduce the vector dot product, which is sort of like a multiplication of vectors, but not really. What does the vector dot product do? Well, the vector dot product takes in two vectors of the same length and produces not a new vector, but a number. And what this number represents is it actually carries information about the angle between the vectors and also their length. As an example, the basic idea of a dot product of two vectors is as I make the angle closer and closer to 0, I bring it closer and closer together, the dot product increases until it becomes the product of the lengths of the vectors. So if this has length L1 and this has length L2, then if the angle is 0, the dot product is just the product of the lengths. So it's just L1 times L2. In the other extreme, if I open up the angle and it comes all the way to 90 degrees and the dot product goes to 0, when the vectors are perpendicular. So it's a measure both of the product of the length of the vectors and also the angle between them. And this is independent of whether they're in 2 dimensions or 3 dimensions or higher dimensions. Well, how do I actually compute the dot product for vectors? Well, it's easy if I have the coordinates of the vectors. And the way I compute it is the sum of the product of corresponding terms in the two vectors, or corresponding elements. So for example, if U is a 3-dimensional vector and it has elements or coordinates A, B, C, and V is also a 3-dimensional vector. Just like vector addition, the vectors have to be the same length in order to compute the dot product. As components D, E, F, then the dot product is the sum of the product of the corresponding elements. So U dot V would be A times D plus B times E plus C times F. The sum of the products of the corresponding elements. And similarly for 2 dimensions or 4 dimensions or 17 dimensions. So this is how we compute the dot product, and its most important basic property is that this answer will be 0 if the two vectors are 90 degrees apart or perpendicular. So let's look at a couple of examples of computing dot products. Let's do one in 2 dimensions. So U is the vector with elements 3, 4, and V is the vector with elements 4 and minus 3. So if I compute the dot product, I have 3 times 4 plus 4 times negative 3. That's 12 and that's minus 12, so the answer is 0. Why did we get 0? Well, if we think about where these lie in the plane, if I again draw a little figure for these two vectors, the first vector with elements 3, 4 is over 1, 2, 3 and up 1, 2, 3, 4. It would look something like this. And the second vector is over 4, but down 3. my picture's any good, you can see that those two vectors are perpendicular or 90 degrees apart, and that's why I got 0 as the answer for the dot product. Let's look at another example in 3 dimensions this time. So U has components 4, 6, -5, and V has components 2, 1, and 3. And so the dot product would be a number computed as the sum of the product of the corresponding terms. So 4 times 2 plus 6 times 1 plus -5 times 3. 4 times 2 is 8. 6 times 1 is 6. And then -5 times 3 is -15. And so 6 and 8 is 14 minus 15 is -1. So the dot product is the number -1 in this case. What's the dot product useful for? Besides testing for when vectors are perpendicular, that's the special case when the answer is 0. As we'll see, the dot product is heavily used in future material. For example, it's used for, as we said, testing perpendicularity. It's used as part of the definition of matrix multiplication. And it's used for forming equations. Using vectors and matrices. So the dot product will have heavy use in future lessons in the class. That's lesson 2.